Hello everyone. Today we're going to be looking at a proof for the division algorithm, which is a basic fact from number theory that can help in a lot of situations. I mean, it's something that's almost obvious to us, but there's a couple details we need to work out in actually proving it, and I think it's a nice example of combining a lot of different proof methods and different strategies. So let's take a look. So let's state the theorem, right? Let a and b be integers and be positive, strictly positive. Then what we claim, maybe in symbols here, is that there exists unique integers, q and r, okay, such that a is equal to bq plus r, and r is a number, could be 0, but between 0 and b. So let's be clear about what we're saying here, right? Pen size is a little bit big. I should maybe bring it down a bit. What we're saying here is it's unique. Okay, that's what that little exclamation point means. So let's look at an example. I think that makes the most sense, right? So if I have the numbers 14, so we'll call A 14, and B is 4, then what I'm saying here is that I can write 14 as some multiple of 4 plus something. So that's definitely true, because let's think about it for a second, right? So let me draw 14 little dots here. Okay, so maybe I could have chosen a smaller number, but so here's 12 and here's 14, I think, right? 4 is 4 is 4, 2 more. And so my claim to you is that we can write this as some multiple of 4 plus something. Well, yeah, we can, right? Because we can just keep subtracting 4 from the number, right? So let's say I keep subtracting 4, keep subtracting 4, keep subtracting 4. Maybe I subtract 4 one more time. Oh, but I got negative. That's the stopping point, right? So all the time here, I'm subtracting 4 repetitively, but I'm still positive. The number is still positive, right? 14 minus 4, okay, 10, positive. 14 minus 4 minus 4, right? It's going to be some, 14 minus 8, which is 6, which is positive still, right? So we, but visually, we keep subtracting 4 from 14 over and over again until I hit a negative number. Oh, okay, I go back. Then yeah, clearly I can, right? How many times could I subtract 4? Well, that's my B. And what do I have left over? That's my R. So 3. Oh, sorry, I mean Q here. My apologies. Q here. So how many times can I subtract 4? That's my quotient. And what do I have left over? That's my remainder. So this implies to us that 14 can be written as 4 times 3 plus 2. Which matches what the statement's telling us, right? Which is that I can write 14, any number, as a multiple of some b plus some remainder. And that remainder necessarily is less than b, right? Because if I stopped here and I said, oh, well, it's positive, right? Stop here and call all that my remainder. Well, I mean, I could do that, but I can do better than that, right? Because my remainder is still bigger than the thing that I'm subtracting by. So we don't like that. We'd like for it to stay smaller than the thing that I'm subtracting by. Because if it was bigger, then I could just subtract one more time, right? If I left 6 as the remainder, then I could just subtract one more time. The thing is that this also works in the negative direction. Okay, right? So in the negative direction, we have a similar thing going on. So we'll maybe look at an example of that, and then we're going to get to the actual proof of this statement here. Proof of this, it's mostly the existence. The uniqueness is not very hard, but the existence takes a little bit of work. Nothing else to really say here. Right? So let's look at another example. Let's say I have negative 14. So A is negative 14 and B is 4. Okay, let's take a look at this. So in this case, I'll kind of draw it as negative 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And maybe we can think of this as 0, and we're like kind of headed in the negative direction, right? The negative direction there. So what we can do instead is we can keep adding 4. Now, however you wanted to demonstrate that, right? So I'm going to remove these 4 negative 4s. So 4 negative 1s, I mean. So it's a total of negative 4. So I'm going to add 4, let's say, right? That's kind of what I'm doing. I'm going to add 4. And I'm going to do this until I become positive. That's always my stopping condition, right? So when I'm thinking about switching from positive to negative, negative to positive, that's what I'm stopping. Here, right, I was always positive, but I stopped when I became negative. Here, I'm going to stop when I become positive. So I can keep adding 4, right? Adding 4. I'm still negative, 2 negatives, right? I can add 4 more, right? And I kind of like go too far, right? So these go away. Maybe I should use a different symbol, right? And I go too far. I added 2 too many. And this, in a sense, is the same algorithm happening, right? I'm taking this negative 14, and now it's negative. I'm going to keep adding 4. So we're going to see how many times can we add 4 until we become positive. Okay. And now I'm going to show that this logic tells us that we can write negative 14, right? The theorem here, the theorem tells us that we can write negative 14 as 4 times something plus something. And that something is going to be, this something right here is going to be between 4 and 0. Actually, not equal to 4, but it could be 0, but up to 4. So, well, yeah, right? Because what we're doing is we're going to keep adding multiples of 4, right? We have this negative 14, right? And how many times, right, could I take away these negative 4? So keep adding 4s, right? Well, I could do it 4 times, right? So if I did that 4 times, right, until I became positive, right? And actually, yeah, a little bit of a difference here is here we stopped. We went back. We said, oh, I became negative. I'm going to go back. Here I became positive. I'm actually going to do it. I'm going to keep it there, right? So 4 times negative 4. So I went backwards 4 steps, right? But then I need to go back this way, however much was left, right? However much was left over. So that would be, in this case, 2. So there was 2 left over there. So negative 14 is 4 times negative 4 plus 2. And yeah, 4 is an integer. 4 is the integer we chose here. Negative 4 is an integer. That's the interesting thing, right? I said q is an integer. I never said q is positive. Q is an integer. So I'm circling here, right? Like the q right there. And then the r just has to be less than b. So 2 is less than b. 2 is less than 4. Has to be less, right? Because if this was bigger, if there was more than 4 left over, then I could have gone 1 more, right? So there was 5 left over. I could have gone 1 more. I could have deleted 4 more or added 4 more, however you want to say it, right? Okay, so that's a little bit of intuition, right, about what's going on here. Maybe just as a final really quick example, right, let's just use A being 6 and B being 3. Then, pretty clear, if B divides A, that means, another way to say that is that I can keep subtracting, right, B, or adding in the negative case, but however you want to say it, until I get precisely 0. And in that case, for sure, right? In that case, for sure, A can be written as BQ plus R, in the sense that 6, for example, can be written as 3 times, well, something, but we know it's possible. So in this case, 2 plus 0, right? With 0 remainder left over. So hopefully it's not too surprising when it divides, then certainly, right? 6 is 3 times 2 plus 0. I think the main thing in this proof that's awkward is the negative side, right? So we're going to try to spend some time on that. Okay, but let's get into the actual proof of the theorem, right? Okay. And I'm going to restate the theorem just so that we have it available to us, right? It's good to always just really try to understand what the theorem is that you're trying to prove, right? You want to use all the hypotheses and everything like this that you have in it. So I'm just going to rewrite it there. Okay, now maybe I'll put a little star around it. Okay, so we're saying if I have a, b in integers, okay, so let's just start with that, right? Maybe I'll change my color here. Let's say I suppose a, b are their integers, right? And of course, b is greater than 0. Then we need to show that this is possible. Okay, so where do we go from here? This next step is really getting into the crux of these examples that we did here. So let's focus on this example here, right? Right, I want to investigate 14 in terms of multiples of 4. Okay, that's what I want to do. 14 in terms of multiples of 4. And in fact, I want to know pretty much, because well, that's kind of what division is, I mean, very, very literally, how many multiples of 4 fit into 14? So I can think of doing, I'm kind of just restating what I did here, but maybe a little bit more algebraically. I can think of like 14 minus 4 times 1. Or maybe even 0. 14 minus 4 times 0, which is 14, right? And then 14 minus 4 times 1, which is 14 minus 4, which is 10. Okay, and I kind of keep doing this. It's kind of what I'm doing here, right? I keep subtracting 4. So another one, 14 minus 4 times 2, 14 minus 8 is 6. Okay, 14 minus 4 times 3, 14 minus 12 is 2, right? Okay, and then 14 minus 4 times 4 is 16. 4 minus 16, which is negative 2, but that is less than 0, right? So we can see that 14 can be written as, well, 4 times 3 plus 2. So it's kind of another way of writing exactly what we just said, right? So you stop when it becomes negative. So we go back a line, we say 14 is equal to 4 times 3 plus 2, right? Just by moving the 4 times 3 over. And the claim here, and so what we want to do is that this will always happen. That we'll always, right, get some smallest value here. It's not surprising to say. I mean, yeah, right? Obviously, right? Oh, shoot, sorry. I'm realizing that you can't see the side of the screen there, so I'm going to just kind of move this over. My apologies. Should be more conscious of that. Well, you still can't see it, can you? Okay, so I really can't use that. Really can't use the side of the screen there. Okay, so I can't go too far. Okay, so sorry, just to recap what I was saying, 14 minus 4 times 0 is 14. I keep subtracting one more value of 4. 14 minus 4 times 1. 14 minus 4 again is 6. 14 minus 4 minus 4 minus 4 is 2. 14 minus 4 is negative 2. I stop there, and I go back one line, right? I go back one line to right there. And we can see that 14 minus 4 times 3 equals 2. Well, I can rearrange it to that. Okay, so again, the claim is that this always happens, that there's always this smallest positive multiple of 4 that I can subtract off of 14. In general, my claim is that there's always a smallest positive multiple of b. It's b, right? Multiple of b that I can subtract off of a. That's kind of where we're going here, right? So maybe I'll write that because that's pretty important. So there is always a smallest value for a minus a smallest positive value for a minus a multiple of, again, you can't see off the side of the screen there, can you? For a minus a multiple of b. So this is not a claim or anything. This is just an idea that we're going to go with because it seems right? So if there's a smallest, I keep 14 minus a multiple of 4 as the smallest value. If I went any lower, it'd be negative. So it's kind of the idea we're going with here. So what we're going to do, and this is the kind of like interesting thing, is that we're going to think about S to be the set of all numbers, basically of all of these numbers, all these ones, all of these numbers. What are those numbers? Well, they're A minus B times K, right? For some integer K, but notably, we want to know that A minus BK is non-negative, right? So we're going to think about the set of all these numbers, A minus BK, where K is an integer, so A minus a multiple of B, but that being a positive number. And again, remember here, the detail is that A could be negative. This is kind of the interesting thing, right? So if A were negative, then we would want to basically be adding multiples of B. So K would be negative, right? If this was negative, then to make this whole thing positive, which is what we're trying to do, right? Remember from the negative example, we're trying to make it positive. To make it positive, we would need a negative K, right? We need to be subtracting, we need to be adding multiples of B. So K would have to be negative, right? To be adding. Okay, we have this set. Okay, interesting, right? So for up here, maybe like if we go back up here, right? For the example of A and B, A is 14, B is 4, then our set S, right, is the set, well, we certainly have 14 minus, I'm going to kind of go up the list, 14 minus 4 times 3, right? Because that's a number that we have in the set. 14 minus 4 times 3, well, that's 2, so that's positive, that's good. Well, not negative. And then we also have 14 minus 4 times 2, right? And we have all these numbers, essentially, right? Because I said it's all these numbers. But it's not the next one. It's not 14 minus 4 times 4. And to be clear, right, we also have 14 minus 4 times negative 10. I don't know. Oop, can't see that, can you? I'll put on the next line. Okay, we have 14 minus 4 times 10 as well. Maybe I'll put like that, right? So, oh, sorry, not 10, negative 10. Negative 10, right? Because we could keep going up this list, right? Up here, Anyways, that's kind of the set there. Maybe for here, right? Let's think a little bit about this example with the negatives, right? Sorry, I don't want to get too cluttered, but I think it's good to talk about all these examples. So the set S is going to be negative 14 minus 4 times something to make it positive. Well, we know that we certainly have negative 4 in there, right? So negative 14 plus 16, essentially, right, is going to be positive 2. And then we also have negative 14 minus 4 times negative 5, right? Negative 5. Okay, so we can keep kind of doing this, right, over and over again. Because this is going to be negative 14 plus 20, and we can keep going kind of in that manner, right? So again, we're thinking about all the results of expressions like this, A minus BK, A minus B times an integer, where that integer might be negative in the negative. If A is negative, then K is negative. But we're thinking about where we want that whole expression to be, at least 0. Okay, so from this set, by evaluating this set, we will show that there are integers, unique integers, Q and R, that satisfy this. And R has the property that it's between 0 and B. Okay, so that's what we're going to do now. We're going to show Q and R exist as, stated, let's say. Which means, integers and R is in the bounds that we said it would be in, right? Like that. Okay, we're just going to start with existence, and then we're going to show uniqueness after, right? That's kind of a separate step. Okay, all right. So let's investigate this a little bit, right? So the first thing that I'm going to claim to you, and actually, you know what? Let me show you where we're headed. Where we're headed is the well-ordering principle. And we're going to take this as an axiom, okay? So we'll just take this as a we're not going to prove this as a claim or anything like that, right? I'm just going to say fact or something like that. Fact. If we have some A, which is a subset of the natural numbers, but let's just say if A is a non-empty set of positive integers, then A has a least element. Hopefully you can read that writing, right? So A has a least element. Yeah, this must be true, right? So if I think of any set, even infinite, right? That's kind of the point, right? Even if I have infinite sets of positive integers, then it certainly has a least element. This is what's called the well-ordering principle. The well-ordering principle. It comes from the way we've designed the natural numbers to work, essentially. Hopefully it's pretty clear, right? So if I have A, which maybe, let's say, is all the even numbers, 6, right? Then yeah, A has a least element, right? 2. 2 would be the least element. Essentially, it's like if I restrict myself to an infinite set of positive integers, I can only go so low, right? That's kind of the idea. I can go as high as I want, right? Because the positive integers, they have no upper bound. There's no greatest positive integer, but there is at least one. And essentially what we're saying is that this applies not only to the integers, to the positive integers, but to any subset of them too. Okay, hopefully that makes sense. There's always a least element. And that element is less than or equal to everything else, right? So I won't write that, but that element is less than or equal to all other elements, or all elements in the set, right? That's the point of a least element. Okay, so that's where we're headed. So my claim is that this is a non-empty set of positive integers. Then it must have a least element. And that least element is going to bring us to Q and R. Okay, so now we're going to basically work with those facts here to kind of help us out. So claim. S is non-empty. Okay, so now we're going to prove the claim. So I'll say proof of claim. Okay, so we know A and B are integers. B is positive. A minus BK is the set that we're working with. Okay, so we say that this is, so for A and B, or any choice of A and B, we're saying that this is always non-empty. Well, if A is greater than or equal to 0, then we're let's say consider A minus BK, right, for some integer K. Well, if A is positive, then of course it's not empty. I could just pick K to be 0, right? K to be 0 would give us A minus B times 0, which is in the form we want, right? 0 is an integer, right? 0 is an integer. And that's equal to A, which we said was greater than 0, or at least 0. So therefore that is in the set. Therefore A minus B 0 is in S. Remember, what do we need to be in S? We need to be in this form, and that form needs to be at least 0. So I can write A, right? I can write this number, A minus B times 0 in the form, and I guarantee you it's positive because I told you A was positive, or non-negative. Okay, well, that's if A is positive. That's pretty easy. So that's kind of maybe step 1. What if, and if A was 0, this would just be 0 minus 0, which is just in the set, right? If A is less than 0, if A is negative, well, then what I'll do is I'll just call A negative absolute value of A. Okay. Hopefully you agree with me here, right? A is negative absolute value of A. And again, we consider A minus BK, and that's going to be negative absolute value of A minus BK. And my claim to you is that I can choose some value of K here that leads this expression, like an integer value of K here that leads this expression to be certainly positive. Well, I can, right? I can for sure. And what that expression is, what that choice for K is the, well, I want that to turn, so I can choose K to be the negative absolute value of A. Yeah. Okay, and let's see why that works. So if I choose that, then I have negative absolute value of A minus B negative absolute value of A. And to be clear, this is an integer, right? A is an integer. So the negative A is a negative integer, so the absolute value of A, whatever, will be a positive number, and the negative, but anyways, it's an integer, right? So I can choose that for K. And then what does this become? This is negative absolute value of A plus B times the absolute value of A. And my claim to you is that this is certainly positive. Okay, this is certainly greater than or equal to 0. So my claim now is that this is actually going to be bigger than this. So what I'm really saying is I'm kind of setting B to 1 there, right? I'm kind of setting B to 1. So let me use a highlighter here. Maybe a highlighter will work, right? I'm kind of setting B to 1. I know that B is at least 1. It could be bigger, but I know B is at least 1. We know that from our hypothesis, right? B is at least 1. So when I replace B with 1 in this expression, I'm certainly making the expression smaller. Unless B was already 1, then I'm leaving it the same, but I'm making it smaller, right? But that's convenient because that is 0, right? Negative A plus negative absolute value of A plus A is 0. And there we have it. There is a choice for K that makes this expression in this form positive, non-negative. Great. So there's our claim. Okay, we have now finally, okay, we've proved that S is never empty. There's always some choice for K in this form, regardless of A and B. And I can always make some choice. Okay. And I had to use the fact. I had to use a lot of facts here, right? I had to use the fact that B was greater than or equal to 1. Okay, so now we have that in our roster, right? We have, just say fact, that we've proven, right? That S is not equal to the empty set. Also, fact, right? S is a subset of the natural numbers, right? We have a non-empty set of positive integers. That means that S contains a least element. That's what the well-ordering principle tells us, right? If I have a non-empty set of positive integers, then S contains a least element. Okay, so now what we have to look into here, right, is how we work with that, right? That's the only detail here, how we work with that. Now, there's a little bit of discussion here about if 0 is contained in the natural numbers or not, right, obviously. So let's actually just deal with that case separately. Okay, so I'll just deal with that as a separate case. In fact, maybe I'll even do it before, just a little higher here. I'll do it right here. So suppose 0 is in S. That means that A minus BK equals 0 for some K in Z. Great, right? That means A is BK plus 0. And we have it. We're done, right? That's what we wanted to show. We wanted to show that there is some Q and R. 0 is certainly less than our K value here, right? Less than or equal to, I guess. Well, it wouldn't be less than. Wouldn't be equal to. And there's our form, right? So we are done. Okay, so that was easy. So that's if 0 is in S. Okay, so from now on we can kind of we can suppose 0 is not an element of S. Okay, so then really, whoever you're talking to, they'll agree with this, right? That was the only point of contention there. Suppose 0 is not an element of S, then we already discussed that S is not empty, but it's also a subset of the natural numbers. So it contains a least positive element, right? That means we have some R in S such that R is least. Call it R. Well, R is in the set, right? So R is equal to A minus BK, but I'll call it Q instead, right? I'm just relabeling it, right? For some Q in Z. Well, okay, great. So now we have it, right? A is just moving that over. We have BQ plus R. Great. I showed, there we go. We did it. I showed that there must be some Q and R that satisfies this equation. The only thing left to show is that R is in the range we want. Technically, I haven't shown that yet, right? I mean, it is, right? Because, I'll show that, but I have to demonstrate it. Right? Show, because that's part of the definition of what we're dealing with here, right? I'm trying to prove that there's some R, Q and R that not only satisfy this equation, but also satisfy this. Okay. So this end is pretty clear, since R is in S, right? We made the set S here. S is a set of all these non-negative numbers in this form. R is in that set, so it is certainly greater than or equal to 0. Great, okay. We don't have to show that, sorry. But all we have to show, right, is show just, R is less than B. I like this proof here because now we take a look at a proof by contradiction. Suppose R is greater than or equal to B. Then we're going to contradict something. And the thing we're going to contradict here is, okay, let's think about it for a second, right? If R, right, is bigger than B, let's go back to our examples here, right? If I left 6 as a remainder here, that means that I could still remove 1, right? If I left 6 as a remainder here, that means that I could still remove another 4. So if that was the case, I don't really have the least element. So that's the contradiction. We're going to show that if this is the case, if R is bigger than or equal to B, then I didn't actually get the least element. But that contradicts the fact that R is the least element, right? And we'll have that. Okay, interesting. Okay, so if R is bigger than B, right? Let's consider the number. Consider A minus B Q plus 1. We're going to call this number R prime. Okay, so I'll write that here. this value is an element of our set S, right? Because it's in the form a minus b times some integer, and q is an integer that we chose, right? We claim the existence of some integer. We're going to consider this number. Okay, well, let's take a look. So I can distribute it in a minus bq minus b. And a minus bq, well, we said that was r, right? We said that was r, so r minus b. Essentially, all I did here was I replaced all that with r. But r is greater than or equal to b, right? So r minus b, I have a bigger number minus a smaller number. Well, that's at least 0. So that means that r prime is in S. And there's a contradiction here. Because we have two numbers in S, right? We have r, so r is in S, clearly. R is the least element. R prime is also in S. But R prime is smaller than R, right? And we'll consider that, right? Show R prime is smaller than R. So let's think about R prime, right? So R prime is a minus b q plus 1, which is less than a minus b q plus 0. Okay. And now in this step here, we have talked about something, but anyway, so then this is less than or equal to, right? Oh, no, not less than or equal to, just strictly less. And that is just a minus bq, which is r. So it's r prime. So we showed that r prime is less than r. And this is a contradiction, right? Since r was least. Write that better. Least. Okay, so we mostly have it. We have shown. Okay, let's think about what we're trying to show, right? So we have a and b are integers. B is positive. We've shown that there exists some q and r such that a is bq plus r, and we've shown this condition. I'll change back to white. We've shown that when I told you how to find this q and r. Well, I told you how to find both of them, right? R is the least element of this set S, and q is the k from that element. And it turns out that r is actually less than b by the construction of that set, and of course positive or non-negative. So what's left? Well, uniqueness, and it's pretty easy. Okay, it's not wildly easy, but still worth discussing. But it is uniqueness. I have to focus on spelling that. It is doable. So what we mean by uniqueness is, suppose A is BQ plus R with R how we want it, and A is equal to BQ prime plus R prime, not the same R prime from before, okay, just that R prime from before was part of the contradiction, right? But different R prime, just a new R prime, with R prime also less than b. Basically, there are two sets of integers, q and r, that satisfy this. Okay, well, we need to show r prime equals r and q prime equals q. That's what we need to conclude, that must be the case. Okay, well, the first thing that we'll say here is, well, if a is equal to bq plus r and a is equal to bq prime plus r prime, well, then those two must be equal, right? So we must be able to conclude that bq plus r is bq prime plus r prime. We can rearrange this a bit. We can say bq minus bq prime equals r prime minus r. And we can say that BQ minus Q prime is equal to R prime minus R. Okay, so this is just getting into a form. And this is a nice form because we see the thing that we're trying to prove, right? We are trying to show that that's 0 and that that's 0. If I can show that, if I can show that that's 0, then we must be able to conclude that that's also 0 because b's not 0, right? So then that must be 0. So really our goal here is to conclude that this actually must be 0, or that R prime minus R is 0, which is, I mean, that's part of what we're trying to show anyways, but that will then conclude that that Q prime is equal to Q. Well, what we can say here, right, is that, this is certainly positive. How do I know that, right? Well, an implicit assumption I can make, and I didn't say this yet, but an implicit assumption I can make, and I'll say without loss of generality, I can say that R prime is bigger than R. Okay, so R and R prime, we're saying that A can be written in these two different ways, but they're not actually different, right? We're going to prove that they must be the same, but supposedly different ways. Well, you're supposedly giving me two different R's here. One of them, they could be equal, but they're either equal or they're not, right? They're either equal or they're not. So if they're not equal, then one's bigger. So call that one R prime. I arbitrarily called it the one R prime, right? So let's just call the bigger one R prime. And that's what without loss of generality means, right? It's like, I'm not putting this isn't really another assumption. I'm not weakening my argument by doing this. It's fine. Like just between R and R prime, one of them is bigger. So call it R prime. So if R prime is bigger, then this is certainly positive. Okay, that's not enough, right? Because I need to show that it is, not positive, but it is certainly non-negative. I now have to show that this is also, less than 0. Less than or equal to 0. So if it was less than or equal to 0, then I would get that it is equal to 0. Okay. Well, we're going to look at this statement right here. Okay, we're going to look at it closely. Q minus Q prime. Q is an integer. Q prime is an integer. Q minus Q prime, integer. R prime, integer. R, an integer. R minus R prime, integer. So this tells us, right, that B can be written, that BK equals R prime minus R. Or that R prime minus R is equal to BK. This tells us that B divides R prime minus R. Right? B divides R prime minus R. Okay, so what, right? I mean, part of the division rule, part of the definition of division. But there's something going on here. B divides this number. Okay, well, let's think about R minus R prime minus R for a second, right? R prime minus R is certainly non-negative, as by our discussion, right? And it's definitely smaller than just R prime, right? Because R is 0. I mean, R is, each of these are non-negative numbers, right? So taking away one of them, it's certainly smaller than R prime. And R prime is less than B. R prime is less than B. We said R prime was less than B, right? R prime is less than B. So that means that B divides a number strictly smaller than itself, right? B divides a number strictly smaller than it is. So it's like if I have 5 divides 4, well, I mean, how could that be? How could something divide something smaller than it? Well, the only way is if that thing is 0, right? Okay, so we're going to prove that as a separate claim here, right? And this is going to be my claim. If B is an integer, and for the sake of our argument, we might as well just say it's non-negative, and A is an integer. But okay, so say A, B are integers. B is positive. and A is less than B. Strictly less than. And B divides A. This implies that A must be 0. Okay, this is my claim. And by this claim, right, we have that B divides a number strictly smaller than it, right? That's what we're saying right here, right? So then this and this in combination tell us that R prime minus R equals 0. In other words, that R prime equals R, right? And kind of working back up here, oops, just choose a color. There we go. Kind of working back up here. Here. If I say now that BQ minus Q prime equals 0, because R prime minus R is 0, well, B's not 0, so Q minus Q prime must be 0. In other words, Q must be Q prime, and we're done. So the proof relies on this claim, right? We have this claim here. And with that claim, we have uniqueness, right, with this statement. Okay, so let's prove this together. Okay, so we're going to prove this claim. I realize there's actually a little something I have to add, so it wasn't true before, but now it's true. So if A, B are integers, I add this condition because that's all we need, right, for our particular purpose. And A is some number. I guess that's necessary for this, right? And you know what? I can combine that into 1. Let's just say I have that. There we go. So in this case, it is true. So let's take a look at the proof here. So we know B divides A, right? So that means that A can be written as KB for some K in Z, right? Okay, so we have this, and we're going to suppose that A is greater than or equal to 1, right? Well, so we're going to contradict this, right? It's going to be by contradiction. Well, if K, our plan here is to show that there's no choice for K, that this isn't true, right? So if K is negative or 0, non-positive, then we have that KB is also non-positive. So certainly KB is not equal to A. A is a number at least 1, right? So you know that. So if K is at least 1, which is the opposite of this, right? K is at least 1, then BK is at least B. But A is less than B, right? So that means that BK is also not equal to A. KB, whatever you want to call it. Well, that's all the options for K, right? Because K is an integer. So using the fact that A is less than B, BK would be strictly greater than B, or equal to B, but A is strictly less. And so it certainly can't be A. And so then we have a contradiction. By contradiction, A must be 0. And that completes the entire proof, the entire thing. Taken as an axiom, as axioms here, we could say the well-ordering principle is taken as axioms. You could say some basic facts about sets taken as axioms, right? The operations on the integers and things like this, right? These are taken as some axioms here, but otherwise it's a pretty self-contained proof here. And hopefully you got something out of it. A little bit of a long video, but hopefully you enjoyed. And if you have any questions or comments on any part of the proof, then please feel free to let me know. Otherwise, yeah, there we go. Thanks so much.